So extrapolation. If you have a formula like that, for example, EDTA, tetraacetic acid, right? Tetra meaning 4, right? So you're going to have 4 protons to the formula, tetraacetic acid. Then the formula will be extrapolated like this. So always start with a 1, okay? And then 1 proton over 1K, start with the last K, Ka4. Then 2 protons, then over 2K, and 3, 4, so on and so forth. Okay, so if you have H3L, then the buck stops here, okay. Now, in terms of magnitudes, whenever you have a plus or minus sign, then you compare for magnitude to see what terms will contribute. Otherwise, nothing wrong. If you have computer, then you can set up a spreadsheet and just calculate all the numbers. If you calculate this by hand, then you should recognize that this 2 is going to be negligible. So to save time, you don't have to involve this 2 in a calculation. Okay, an example is this, tartaric acid. Now, it is an acid, and itself is a complexing agent, okay? So, look up the table, the 2 Ka values is that. So now, if you dissolve into a solution, a buffer for pH equal to 5.0. So this tells you that the free proton concentration is 10 to the minus 5 in the solution. Okay, so this is fixed for you. Then you are asked to calculate the beta, what fraction of complexing agent will be available. So you remember this formula, okay, then the pH indicates is 10 to the minus 5 concentration. Okay, then you plug in like that. Then notice the math here, first one, second one is 0.23. Notice the third one becomes negligible. Okay, so it's virtually the same as 1.23. So you recognize this, then you ignore this calculation, then you save another 2 minutes on your exam. Okay, then just use the 2 terms. Now, a fraction cannot be greater than 1, right? And you know that this is not your final answer. Okay, then you recall, oh, okay, the reciprocal, then I get the fraction. So if 81% at pH 5, 81% will become complexing agent. Okay, beta. Okay, then I'll revisit some knowledge you already know. The titration curve. But now is the titration between strong base and weak acid. So the weak acid, let's say you 10 to the minus 5. Let's say you HA, the acid is your analyte, and we have 100 millimoles of your analyte. Now, if you are asked to calculate the titration curve for the to make the titration curve, then that means you need to calculate for the pH of the mixture. So basically, there are 3 regions again that you learned previously. So the kind of calculation before the endpoint. Before meaning you have excess analyte. Okay, so all you need to know is this concentration. Then proceed with the Ka expression and calculate. Now at the end point, once you are at the end point, there's no excess. So that means you have just one chemical only. So we will deal with that chemical carefully later. need to recognize this carefully. After the endpoint, you're going to add excess hydroxide. So whatever the quantity of this excess will dictate for the pH or the pOH. Okay? So now we are ready to go. So the starting pH, so the first data point on the curve, then that means you have HA only. So the Ka expression is like this. Okay, then you know that, you set it up like this. Then this X is negligible, so it's reduced to something like this. Okay, so pH equals 3.0, so to begin with, before you add any titrate, pH equals 3.0. Okay, so now you start to add sodium hydroxide. Once you add sodium hydroxide, you're going to generate this corresponding salt, right? You start with a weak acid, and now you generate corresponding salt. Then that is a formula for buffer. When you have the two chemicals, then that is your buffer. So you will expect a flat region called the buffer region on your titration curve. So let's say you add 10 millimoles of the titrate, sodium hydroxide, equivalent to 10 millimole. Then you know that this is before the endpoint, right? You have 100 millimoles, so it's far away from the endpoint. So the Ka is still expressed like this, but now you have the buffer ratio, right? Remember your buffer ratio in the buffer rate region, so would facilitate to think along that line, right? So this is generated salt, and this is a remaining acid. So this is the pair, right? So this is your buffer pair. So 10 millimoles reacted, you have added 10 millimole, and therefore A minus is your product, right? It's generate 10, and 90 remain because of 100 to begin with. Okay, so you would be able to do that, right? So 100 subtract 10 is equal to 90. And this is 0 plus 10, so it's equal to 10. Okay, so your buffer. So now this data point is 4.05. Okay, similarly, if you add a total of 20 millimoles, then same. Before the endpoint is buffer. So same formula applies. And then this ratio change. You know that, you generate 20. And here's 100 minus 80. So, etc. So you can do the math. Now, once you add 50 millimoles, it's right in the middle of the buffer region. So this region is particularly cool. So this 2 will be equal. So this 2 equal. So the X is equal to 10 to the minus 5. So what it amounts to, the pH in this region is equal to pKa. So this particular point is useful to identify an unknown acid, knowing what it is, right? So you simply titrate your unknown, and construct a titration curve. Then you go to the middle. Okay, middle, then you read off the pH. Then from this pH, then you get the pKa. So that from the pKa, you get the Ka. Then you go back to the Ka table, right, to get the closest match. Okay, then you will find, oh, this Ka, oh, acetic acid, yes, that's what it is. Okay. That kind of thing. So there's a particular useful region. Any question with that? Now, exceed the 50 millimoles, still less than 100 millimole, that means it's still before the endpoint. So still a buffer, right? So you go like this. So 80, 0 plus 80 is equal to 80, then 100 minus 80 is equal to 20. So this kind of ratio, then you solve the x and then change the x into pH. Any question with that?